This talk is about revisiting scaling laws for robotic mobility in granular media. These scaling laws, a recent development in granular mechanics and vehicle engineering, are the result of using dimensional analysis to address a wheel traversing deformable terrain. There's great potential to use these laws in the development of robotic vehicles such as rovers, and we designed a series of experiments to explore how different changes to the vehicle might affect the output. We first formed the functional expression for a wheel traversing a bed of granular media. The dependent variables of interest are the required mechanical power P and the translational velocity V. Power and velocity are a function of unknown form psi of the independent variables. These independent variables are labeled on the image seen here. The wheel is described by a characteristic length such as its radius L, its thickness or depth into the page D, its mass M, a driving rotational velocity omega, and a shape outline F. The shape outline sets the condition that although the wheel shape may be arbitrary, it must be consistent when scaling. We could not, for example, predict a grousered or lugged wheel and predict results for a smooth wheel. The environment is described by time t, gravity g, granular bulk density ρ, internal granular friction μ, and wheel grain friction μw. The granular properties must also be consistent. Results from different granular environments cannot be compared. Using dimensional analysis and a careful set of assumptions, a new psi function is depicted here. This states that a non-dimensional power and velocity are functions of the given values we've transformed. Note that this has left us with only our chosen wheel parameters and time within the function. We also note that the characteristic length and mass are the two parameters outside of the function which we may change. We therefore choose to scale them by r and s. This will lead to an expression seen here. The prime set of the parameters are selected such that d and omega balance our changes to L and M to maintain the same value within the function, which maintains its output value despite the unknown shape. We now choose power as an example of how this will make prediction possible. We rearranged our second equation to show the relationship with the original value of power here. If a prime set of parameters are applied, that is, a different wheel radius and mass with the appropriate changes made to thickness and angular velocity, then the p prime function takes on a new form. Importantly, these prime parameters are chosen such that the psi value is identical in equations 4 and 5. This leads to the relationship seen between p and p prime in equation 6 and shows how we can predict the values. Two sets of wheels are used in the experiments. The sandpaper grit is 80 grit and matches that of the original Slonaker et al. Paper. And the grouser shape is used as this is a common rover wheel shape. The grouser design was driven by an equation which ensured full grouser effectiveness. The full set of parameters is listed in the paper. In the context of the previous slide, the GSL2 sizing would be the wheel with the prime parameters. The experiments were performed in Quickcrete silica sand, which is the sand of the original Slonaker et al. Experiments, and the weights were varied for each pair. We did this with both wheel shapes, and after each trial, the sand was tilled with a thatch rake in the direction of travel to prepare the sand consistently for each experiment. This was done to eliminate any local stress concentrations and will be important later. The power between two scaled sets can always be expressed as a ratio. Given the relationships that we chose between GSL1 and 2, the predicted power of the GSL2 sets should always be at a ratio of 2.05 to that of GSL1. This was not the case observed. A mass dependency was noted, with the mass of the larger pair seen here on the x-axis and the power ratio on the y-axis. This can be expressed alternatively as an error percentage function of mass. Running a linear regression, it is estimated that the heaviest mass would need to be at 8 kilograms to attenuate the error to 0, beyond the ability of the vehicle as it was built. However, this mass dependency still warranted investigation as this was not predicted, so additional experiments were performed. These experiments were performed to examine the sinkage of the wheels in the environment during trials. This was done with both wheel shapes using the larger GSL2 sizing for each shape at the largest and smallest masses and at the slowest speeds to control for any inertial errors. These tests were performed with both the raking preparation and with a smooth leveled surface. A sliding rigid bar used with an attached caliper measured the difference between the peaks and valleys of the raking pattern, as well as measuring the sinkage. Two effects are seen here. First, the depth of the raking pattern on the surface is of comparable magnitude to the sinkage. This leads us to conclude that this likely contributed to the scaling deviations. In particular, as a result of raking, the grain packing fraction was altered within the range of sinkages observed. This may have changed the effective friction of the granular media to a degree and violated the assumption of the environment having a consistent friction coefficient. It may have introduced some level of surface effects to density as well. Second, in unraked trials, the sinkage was even shallower. Given the particle size of the Quikrete sand is generally between 300 to 800 microns, the depth observed, only a few grain sizes, is likely too shallow for predictable response and to avoid any significant surface effects. This likely causes sand response to deviate from the frictional plasticity of a continuous block, which underpins the scaling theory. Two more variables were observed to affect error. The first is the difference between the leading and lagging motors in the Grousered wheels. This is an area where our experiments notably diverge from the original Slonaker ones. If the two wheels are treated independently and the power ratios of the leading and lagging wheels are evaluated separate, some important trends emerge. The rear wheel shows far less error than the front wheel. Given the observations about the sinkage and preparation, it is likely that the front wheel prepared the sand in a more uniform manner for the back wheel. This is one area which warrants further exploration if these laws are to be used with 2- or 4-wheeled vehicles. Finally, we note a velocity dependence in the air. Expressed again as power ratio, it is most prevalent in the heaviest cases. Remember, the power ratio we're aiming for in all experiments is 2.05. For the heavy sandpaper wheels, seen in black triangles, 13 RPM results in only 3% observed error. If we trace over to 65 RPM, we see that this has now become a 17% error. If it is desired to implement scaling predictions for vehicles beyond the typical slow rover speeds of below 1 km/h, this is an area which needs to be investigated. It is also unclear whether this effect will be more pronounced the further a wheel shape deviates from cylindrical, such as a lugged wheel. To summarize, granular scaling laws were revisited for the case of a lighter, faster, 2-wheeled vehicle with 2 wheel types. These wheels carried an order of magnitude less mass than the original experiments and rotated an order of magnitude faster. At the rotational velocities of 13 to 75 RPM and 1.5 to 5.2 kilograms, several unanticipated deviations from the laws were observed. These deviations were dependent on the angular velocity, the mass, and the wheel placement. Additional experiments indicated that shallow sinkage alone and combined with the sand preparation pattern of similar magnitude to the sinkage likely disrupted the assumptions underpinning the theory, explaining the mass dependency. This leads to recommendations of a smooth uniform testing surface and first-order sinkage observations to ensure that the test vehicle will achieve sufficient depth. Deviations dependent on angular velocity can be investigated for future use of these laws in vehicles. Some vehicles, such as Mars rovers, may only travel at speeds of a few centimeters a second, and in this case the inertial effects will likely be trivial. For some terrestrial applications, they may be more significant. Differences in the front and rear wheels should also be investigated for use in future vehicle testing. It is unclear whether the effects seen here will be as pronounced with an already smooth surface and sufficient sinkage. Finally, granular behavior is material dependent. A good next step is to investigate environments of interest. This may include lunar or Martian simulants or specific industrial application in fields such as mining or construction. While there appear to be some limitations and further investigation is needed, we conclude that these laws can become a powerful tool for vehicle engineers and roboticists alike with careful application and future investigation.